Welcome everyone to the free DCET coaching conducted by the Department of Mechanical Engineering, MIT Tandavpura, Mysuru, in association with the Maharaj Institute of Technology, Mysore, MIT Mysore. Myself, Professor Yashwant SV, Department of Mechanical Engineering, MIT Tandavpura. Now I am going to discuss the chapter 4 of DCET syllabus, that is fluid mechanics and pneumatics. Right? These are all the course content or the topics we need to study for the preparation of the DCET related to the chapter 4, that is fluid mechanics and pneumatics. Right? Initially, we are having properties of fluids, different properties of the fluids, and manometers, differential to manometers, means the pressure gauges, different types of flows, Bernoulli's equation, different flow measuring devices like venturimeter, orifice meter, hydraulic coefficients, Darcy-Weisbach equation, Chayes equation, hydraulic gradients, then the pumps, reciprocating pump, centrifugal pump, hydraulic systems, and pneumatic systems. Now, I am going to in this chapter I'm going to discuss this much contents. Then we'll go for the another topics, that is pumps, hydraulic systems, and pneumatic systems. Okay. Now, before going for the properties of the fluid, we need to understand the definition or the meaning of the word fluid. This fluid can be defined as a substance which undergoes continuous deformation under the action of shearing forces, however small they may be. We are having three states of matter: solids, liquids, and gases. Out of these three matters, different states of matters, we are going to call liquids and gases commonly as fluids. Why? Because if we apply any of the deformation force on solids, the solids undergoes deformation within the elastic limit, and if we remove the deformation force, it will regain its initial shape and size. But if we apply a similar deformation force on the liquids and gases, it will never ever regains its initial shape and size. Means it will undergo the continuous deformation. That's why we are going to commonly call liquids and gases as the fluid, or generally anything which flows can be called as the fluid, right? Conversely, if the fluid is at rest, there will be no shearing forces acting. Means for the fluid which is at rest, for an example, a cup of coffee in front of you or kept on the table, for this coffee, all the forces acting on this coffee are in the vertically downward direction, that is the weight. There will be no shearing forces. That's why that fluid is in rest. Generally, liquids and gases are considered as the fluids. Then we need to understand the meaning of the word mechanics. Mechanics is a branch of science which deals with the study of objects or the bodies at rest as well as in motion. Now let us combine the meaning of two different words, fluid and mechanics. As fluid mechanics is a branch of science which deals with the study of behavior or the characteristics of the fluids either at rest or in motion. We are going to classify we are going to divide this wide branch fluid mechanics into three divisions. First one is fluid statics, means it will go into study the characteristics of the fluids at rest. Next, we are having fluid kinematics. It is going to study the behavior of the fluids in motion without considering the force and energy causing such motion. Then we are having fluid dynamics. It is the branch of fluid mechanics, deals with the properties of the fluids in motion by considering the force and energy causing such a motion. Next, the first property of the fluid is the density or mass density. It is defined as the ratio of density mass of the fluid to the volume of the fluid. That is m by v will gives you the density of the fluid. It will tells us, if we consider 1 meter cube volume of any fluid, it is going to then it will have how much of mass it is going to occupy. It is the mass by volume. Mass per unit volume is nothing but the density denoted by the symbol rho and expressed in the unit, expressed with the unit kg per meter cube. The density of water is 1000 kg per meter cube and density of air is 1.23 kg per meter cube. Next property is weight density or specific weight. It is defined as the ratio of weight of the fluid to the volume of the fluid, right? And its unit is Newton per meter cube. For mass density, if you multiply 9.81, then it will gives you the value of weight density. Then third property is the specific volume. It is defined as the ratio of volume of the fluid to the mass of the fluid, or it can also be defined as the reciprocal of the mass density, and it is having the unit meter cube per kg. Next property is specific gravity or the relative density. The specific gravity or relative density is defined as the ratio of mass density of the given fluid to the mass density of the standard fluid. For liquids, water is taken as the standard fluid or considered as the standard fluid, and for gases, air is considered as the standard fluid. Mathematically, specific gravity is noted by the capital S. Specific gravity of liquids is given by weight density or mass density of the given fluid to the weight density or mass density of the water. Similarly, for gases, we are going to define the specific gravity. Then cohesive force and adhesive force. If the force of attraction is between the molecules of the fluids or the molecules of the same fluid, then it is called cohesion. If the force of attraction is between the molecules of the fluid and the molecules of the other substance, means the molecules of the container, then we are going to say that or call that force as an adhesive force. Next one, viscosity. Viscosity or dynamic viscosity is defined as the property of the fluid which offers resistance to the movement of one layer of fluid over the another adjacent layer of the fluid. Now, suppose let's consider a fluid flowing over a stationary flat surface or stationary flat plate. Because of the no-slip boundary condition, means because of the adhesive force between the first layer of the fluid and the surface of the solid, first layer of the fluid elements gets adhered or stick on to the solid surface. Therefore, no-slip boundary conditions occurs here, and the velocity of the fluid particles which are in contact with the solid surface will be zero. Now, if we move in the upward direction, the velocity gradient occurs, means the velocity increases. Let us consider two layers which are separated by the small distance dy. Let the bottom layer is having less velocity, lower velocity u, and the top layer is having the higher velocity u plus du, then the difference in velocity will be du, right? Now, in this case, bottom layer is going to exert resistance for the flow of top layer. In turn, top layer is going to exert resistance for the movement of the bottom layer. Now, this resistance, along with the viscosity of the fluid, causes the shear stress tau, and that shear stress tau is directly proportional to the velocity gradient du by dy. Du is the change in velocity, dy is the small distance between the layers, and this shear velocity gradient is directly proportional to the shear stress, or this shear stress is equal to mu into du by dy, where mu is the proportionality constant called the coefficient of dynamic viscosity, right? Or mu is equal to tau into du by dy. And we are going to call this law tau is equal to mu into du by dy as Newton's law of viscosity. Okay. And the units of viscosity. The SI of viscosity is Newton second per meter square or Pascal second, and CGS unit is Boyce, right? Next, kinematic viscosity. Kinematic viscosity is defined as the ratio of dynamic viscosity of the fluid to the density of the fluid. Right? It is denoted by the symbol nu, nu. And it is having the SI unit meter square per second and CGS unit Stokes. Variation of viscosity with temperature. The viscosity in fluid arises mainly due to two reasons. One is cohesive force between the molecules, and another one is molecular momentum transfer. Now, let's consider the case of liquids. In liquids, these cohesive forces dominates the molecular momentum transfer. Means the cohesive forces are very much higher in magnitude compared to the molecular momentum transfer. Now, if I supply some heat to the liquids, then the molecules tends to move far away from each other because of the increase in kinetic energy of the molecules. Then the cohesive forces decreases. Hence, for liquids, the viscosity decreases with increasing temperature. ಅದಕ್ಕೆ like that we came across this phenomenon. If I consider coconut oil, in winter season the coconut oil is very thick. In summer season coconut oil is very thin because of the viscosity decreases. In case of gases, this molecular momentum transfer dominates the cohesive forces. Now if we supply the heat or increase the heat, then molecules tends to move randomly. Thereby the molecular momentum exchange increases. Thereby the viscosity of the gases also increases with increasing temperature. Then Newton's law of viscosity, already we discussed while discussing the Newton's viscosity concept. This shear stress tau is directly proportional to rate of shear strain or velocity gradient du by dy in bidirection. Then the classification of fluids. Based on the variation of shear stress tau with respect to the viscosity, we are having different types of fluids. Ideal fluid, which is an hypothetical fluid, which is incompressible, right? Compressible means if we can compress the fluids, those are all called the compressible fluid. All the gases are considered as compressible fluids, and all the liquids are considered as incompressible fluids. A fluid which is incompressible and having no viscosity is called the ideal fluid. Real fluid, all the fluids which are in our day-to-day interactions are called the real fluids. Newtonian fluid, which obeys Newton's law of viscosity. Non-Newtonian fluid, which doesn't obey Newton's law of viscosity. Uh, the variation in viscosity, the dependence or the relationship between the viscosity and shear stress for the non-Newtonian fluids is given by the power law, that is tau equals k into du by dy whole raised to the power of n. For Newtonian fluids, where the value of n, that is flow behavior index, is equal to 1, and the value of k, consistency index, is equal to viscosity mu. So this graph is going to will gives us the variation of viscosity with the shear stress for the different fluids. Next property is the surface tension. The surface tension is defined as the tensile force acting on the surface of the liquid in contact with the gas, or on the surface between the two immiscible liquids, such that the contact surface behaves like a membrane under tension. Right? The surface tension, the value of surface tension for air-water interface is 0.073 Newton per meter, and air-mercury interface is 0.48 Newton per meter. Okay. Now the another property is the pressure. This pressure is nothing but the force acting on the area, or force per unit area is nothing but the pressure, right? Fluid pressure at a point. Pressure or intensity of pressure P may be defined as the force exerted by the fluid on the unit area. It is denoted by P and given by P is equal to F by A, where P is the intensity of pressure, F is the pressure force, and A is the area, solid area. Right. Next, let us discuss Pascal's law. This Pascal's law states that pressure or intensity of pressure at any point in a static fluid is equal in all directions. Means, in a static fluid, means for a fluid at rest, if I consider any point, at that point the pressure is equally distributed in all the directions. That is Px equals Py equals Pz. We are having the derivation of it. Let us discuss another law, that is hydrostatic law, or how this law gives us or tells us how the pressure is going to vary with the depth, or if we move deeper and deeper or in the downward direction in a static fluid, how the pressure increases or how the pressure changes. Right? It states that the pressure at any point in a fluid at rest is obtained by the hydrostatic law, which states that the rate of increase of pressure in the vertically downward direction must be equal to specific height, or the product of mass density into acceleration due to gravity, that is rho g. That is, see here the mathematical expression del p by del z means the rate of increase of pressure in the vertically downward direction z is equal to rho into g. Or if I integrate this equation, then we are going to get p is equal to rho g z, where z is the depth. Means pressure increases if we move deeper and if we move in the downward direction, and increase in pressure or the pressure at any point in the static fluid is given by the hydrostatic law, that is P is equal to rho g h or rho g z. Okay, then the types of pressure. We are having four types of pressures. First one is the atmospheric pressure. This is the pressure exerted by the atmospheric air on all the surfaces which are in contact with it. That is usually its numerical value is 1 bar. Next one, gauge pressure. This pressure, this is the pressure measured using any of the pressure measuring devices, right? And all these pressure measuring devices are going to consider this atmospheric pressure as their reference, right? Next one, absolute pressure. This is the sum of atmospheric pressure and the gauge pressure. Then the vacuum pressure is the pressure below or less than that of the atmospheric pressure, right? Here we are having mathematical expression. Absolute pressure is the sum of atmospheric pressure and gauge pressure, and vacuum pressure is equal to atmospheric pressure minus absolute pressure. This figure will give you clarifies everything, right? Next, measurement of pressure. Now, this pressure can be measured using pressure. Many of the pressure measuring devices, these pressure measuring devices can be classified into two types. First one is manometers, second one mechanical devices. Now, in fluid mechanics, we are going to discuss these pressure measuring devices, that is manometers. So, manometers are the devices used for measuring the pressure at any point in a fluid by balancing the column of fluid by the same or the another column of liquid only. These are classified into two types: simple manometers and differential manometers. Simple manometers. A simple manometer is one which consists of the glass tube whose one end is connected to the point where the pressure is to be measured and the other end remains open to the atmosphere. A few important types of simple manometers are piezometer, U-tube manometer, and single column manometer. Piezometer. It consists of an L-shaped glass transparent tube whose one end is open to the atmosphere top end. Another end is connected to the point where we need to measure the pressure. As soon as we connect this L glass tube to the point where we need to measure the pressure, then the liquid starts to rise in this column. By measuring the height of the liquid column in this tube, we can measure the pressure by applying hydrostatic law, that is P is equal to rho g h. The second one, U-tube manometer. This consists of an U-shaped transparent tube whose one end is connected to the point where we need to measure the pressure and other end is exposed to the atmosphere. And in this glass tube, we are going to fill one heavier liquid, whose density is higher than that of the liquid whose pressure needs to be measured. Usually, we are for the measurement of liquid water pressure, we are going to fill this manometer by the heavier liquid, that is usually mercury. Suppose rho 1 is the density of the water whose pressure needs to be measured, and rho 2 is the density of the manometric liquid. Here, let us consider one x axis, that is the manometer axis ಅಂತ ಒಂದನ್ನು ಕನ್ಸಿಡರ್ ಮಾಡ್ಕೋಬೇಕಾಗತ್ತೆ, and that must be at the interface of two liquids. Here, this is the interface of two liquids. Now, before connecting this manometer, U-tube manometer to this U-tube to the pipe where we need to measure the pressure, the level of mercury in both left limb as well as right limb will be same, because at both the limbs atmospheric pressure is acting. As soon as we connect this U-tube to the pipeline or the point where we need to measure the pressure, if the pressure at this point A is higher than the atmospheric pressure, then on in the left limb, this liquid is going to push the mercury downwards. In turn, the mercury level rises or increases in the right limb. Right? Now, in order to analyze or in order to calculate the pressure, we need to learn how to write the manometric equation. Now, see here, this is the manometric equation. Pressure in the left limb must be above datum xx must be equal to pressure in the right limb above xx, means xx axis. Now let us start from the point and end at the axis. Here also start from this point and let us end at the axis. What is the pressure at point A? That is PA is the pressure. Now pressure doesn't varies along the horizontal axis, therefore till this point the pressure is PA. We are moving the downward direction, therefore pressure increases, that is PA plus pressure increase ಆಗ್ತಾ ಇದೆ, ಅದಕ್ಕೋಸ್ಕರ ಪ್ಲಸ್ ಅಂತ ಹೋಗುತ್ತೆ. ಎಷ್ಟು ಇನ್ಕ್ರೀಸ್ ಆಗುತ್ತೆ? ರೋ ಜಿ ಹೆಚ್ಚು ಇನ್ಕ್ರೀಸ್ ಆಗುತ್ತೆ. ದಟ್ ಈಸ್ ಹಿಯರ್ ದ ಡೆನ್ಸಿಟಿ ಈಸ್ ರೋ 1 G H1. That must be equal to, here the pressure is atmospheric, the gauge pressure is 0 here. If we move downwards, pressure increases by the amount rho G, rho 2 G H2. Here this is the equation. PA, pressure at the point A, plus means we are moving in the downward direction, rho 1 G H1, that is equal to rho 2 G H2. Likewise we can measure the pressure using U2 manometer. The second type is that you are having in your syllabus is differential U2 manometer. This is very much simple. Differential, this type of differential U2 manometers are used to measure the pressure of at 2 points, and this differential U2 manometer is going to give the difference of pressure between these 2 points E and P. Here this consists of one U-tube glass tube. One it is connected to the point A, another one is connected to point B. Right? We are having one manometer liquid, rho m. Rho 1 is the density of the fluid which is flowing in this pipeline, and rho 2 is the density of the fluid which is flowing in the right side pipeline. Similar, let's consider on x-axis, pressure in the left limb above x must be equal to pressure in the right limb above x. At this point, pressure is PA. Right? Here also pressure is PA. We are moving in the downward direction, right? Therefore pressure increases plus. How much increases? Rho 1 G H1 plus H. Then on RHS, right hand side, the pressure is PB. Till this point the pressure is PB. Then moving in downward direction, plus rho 2 G H2. Again moving in the downward direction, rho m G H. Right? See here, that is we are having here PA plus rho 1 G H1 plus H is equal to PB plus rho 2 G H2 plus rho m G H. Likewise we can measure the pressure, difference in pressure between the 2 points. Right? Okay, let us discuss fluid kinematics, the different types of flow. First one, steady flow and unsteady flow. Steady flow means it is defined as that type of flow in which the fluid characteristics like velocity, pressure, density, etc. at a point does not changes with respect to time. Means if the properties of the fluid remains constant with respect to time. Means for example, at this moment of time, I am having the velocity of fluid as 5 meter per second. The next time interval also, if it remains the same, then we are going to say the flow is steady. Unsteady means if the characteristics of the fluid changes with respect to time, that is called unsteady flow. Next one, uniform and non-uniform flow. If the velocity of the fluid does not changes with respect to spatial coordinates or the location or different locations, if the velocity remains the same, then we are going to say that flow as an uniform flow. Velocity changes from point to point, non-uniform flow. Compressible flow. A compressible flow is defined as the type of flow in which the density of the fluid changes from point to point. In other words, if the density does not remains same, constant, then that flow is called a compressible flow. Incompressible flow means the density remains same, then we can call that as an incompressible flow. Laminar flow. It is a type of flow in which fluid particles move in a well-ordered manner or the path, or we can call that well-ordered path as a streamline. Next, the turbulent flow. It is a type of flow in which fluid particles move in a random zigzag manner. Right? In order to differentiate between the laminar flow and turbulent flow, we are going to define one non-dimensional number called Reynolds number. It is defined as the ratio of inertia force to viscous forces for and it is of the order of rho Vd by mu. For circular pipes or for the fluid flowing in a circular pipe, if the value of this Reynolds number is less than 2000, it is called as a laminar flow. If it is greater than 4000, turbulent flow, or if the value of Reynolds number lies between 2000 to 4000, then we can say the type of flow is a transition flow, means the flow is getting shifted towards from laminar to turbulent. Rotational flow. Next one. Rotational flow is defined as the type of flow in which the fluid particles rotate about their own axis. Means we are having the rotational components or the rotation angular velocities came into picture. If there is no rotation of the fluid particles, irrotational flow, then we are having last one dimensional, two dimensional, three dimensional flow. If any of the fluid characteristics changes or varies with respect to only one spatial coordinates x, let's say x direction, then we can say one dimensional flows. If any of the properties changes with respect to two spatial coordinates x and y, two dimension. Three, if properties changes with respect to three dimensions or the three coordinates, three dimensional flow. Okay. Next one. Next, we in our syllabus we are having Bernoulli's equation, right? Okay, this Bernoulli's equation tells us that this Bernoulli's equation can be obtained by integrating the Euler's equation. And this tells that total energy at any point in a fluid remains the same. And this total energy consists of three different parts of energies, that is pressure energy, velocity, kinetic energy, and datum energy. This P by rho G represents the pressure energy per unit volume of the fluid, or we can call this as pressure head, P square by 2g. Kinetic energy per unit volume of the fluid, or the kinetic head, and said datum head or datum in potential energy per unit volume of the fluid. If we add all these three energy components, that then that value must be a constant, right? Now let's discuss Bernoulli's. We understand the Bernoulli's principle or the Bernoulli's theorem. This is applicable only for the ideal fluids. Okay. Now let us consider two different points, 1 and 2. Let us consider the fluid is flowing from point 1 to point 2. Now, this term gives us the total energy at point 1, that is P1 by rho g plus V1 square by 2g plus Z1 will gives us the total energy at point 1. This must be equal to total energy at point 2, that is P2 by rho g plus V2 square by 2g plus Z2 plus HL, where HL is the loss in head of the fluid while flowing from point 1 to point 2, if and only if the fluid is real, if there is having fluid is having some viscosity, right? And this Bernoulli's principle can be used for the measurement of flow. And the first flow measuring devices what we are having is an venturimeter. This is an flow measuring device. We need to insert this venturimeter in a pipeline, and it consists of three parts: short convergent section and throat, and a long divergent section. And we are connecting one U-tube manometer between inlet and the throat. By measuring the difference in pressure, we can measure the discharge or the amount of fluid, right? And this is the equation to measure the theoretical discharge using an venturimeter, that is Q is equal to A1 A2 square root of A1 square minus A2 square into root 2GH, where A1 is the cross-sectional area at the inlet and A2 is the cross-sectional area at the throat, and H is the difference in mercury level. And for actual discharge, we need to multiply this theoretical discharge by CD, and the value of CD is always less than 1. For venturimeter, the value lies between 0.95 to 98. Then we are having another one flow measuring device, that is an orifice meter. This orifice meter consists of a circular disc having a hole, maybe at the center or different locations, right? Here, A1 is the area at the inlet, and A0 is the area at the area of the orifice or the hole. By applying Bernoulli's principle, we can obtain this equation, that is Q is equal to CD, the actual discharge is equal to CD times of root 2GH A1 A0 square root of A1 square minus A0 square. Okay, let us start next topic, that is loss of head or energy in pipes. When a fluid is flowing through a pipe, fluid experiences some resistance to its motion because of the viscosity, right? In turn, there will be some part of energy present within the fluid lost in order to overcome that resistance. Now we are having two types of losses: major head losses and minor head losses. If the loss in head or the total energy of the fluid is due to friction between the flowing fluid and the interior surface of the pipe, then we are going to say that loss as a major head loss. If the loss in head due to friction occurs because of any other pipe fittings, then we are going to call that as an minor head losses, right? Now we are having two equations to determine the major head losses. First one is Darcy-Weisbach equation, and second one is Chayes equation. Now we don't have any derivation in our syllabus. Let us directly go for the final equation. The head loss due to friction HF is given by 4FLV square divided by D into 2G. This is known as the Darcy-Weisbach equation, where HF is the head loss due to friction, 4 is constant, F is the friction factor that can be obtained from Moody's plot for a given velocity and the diameter of pipe and the Reynolds number. And L is the effective length of the pipe, and V is the velocity of the fluid, D is the diameter of the pipe, and G is the acceleration due to gravity. Okay. Next one, Chayes equation. This Chayes equation is given by V is equal to C into square root of M into I, where V is the velocity of the fluid, C is the Chayes constant, and it is given by square root of rho G by EF dash, and I is the head loss per unit length, HF by L. And in order to estimate the value of F, we make use of a Colebrook equation, we make use of Moody's plot, right? These are all the two losses. Okay, let us discuss different types of. This is the Moody's plot. So here we are having the values of friction factor, and and here we are having relative roughness of the pipe. Okay, next minor losses. If the loss of head due to sudden contraction like this, see here, this is the diameter of the pipe, and this is a sudden increase in diameter. This is a sudden enlargement, sudden expansion. The loss of head due to sudden expansion is given by V1 minus V2 whole square divided by 2G, where V1 is the pipe, the velocity of the pipe at the smaller section, V2 is the velocity of the fluid at the larger section. Loss of head due to sudden contraction, that is H contraction is equal to 0.5 V square by 2G, where zero point 0.5 is the constant K, value of K. Similarly, for entrance of pipe, at the entrance of pipe, some minor loss will be takes place. Place given by 0.5 V square by 2G at exit, and because of some obstructions like any wall or whatever it may be. Then for obstructions, this is the equation to calculate the loss in head. Okay. Then loss of head due to bend in the pipe, that is K. This the value of K depends on the pipe roughness factor or the bend, type of bend, different fittings. Okay, this is all about major and minor losses. Okay, with this we completed the discussions on properties of fluids, types of fluids, Bernoulli's equation, Venturi meter, orifice meter, major losses, minor losses, all those things we discussed. Thank you.